Okay, so today we're going to talk about nuclear chemistry. We're going to calculate the nuclear binding energy in joules and the binding energy per nucleon for the following isotope. And what we have here is plutonium. All right. So first thing I want to talk about is it says calculate the nuclear binding energy here. Okay, so that's what we're going to want to find our nuclear binding energy. Now, nuclear binding energy is the energy required to break up a nucleus into its components, or component protons and neutrons. So let's just keep that in mind as we're doing this equation. That's exactly what we're trying to find out. Okay. So here, what we have is our plutonium, and we have our AMU, atomic mass units. And the first thing we're going to look at is our plutonium here. Okay, so our 94 on the bottom here is going to stand for our protons, and here is going to be our nucleons. So our top number is going to be our nucleons, our bottom number is going to be our protons. And the first thing that we're going to want to do is find our neutrons. And the only way to find our neutrons, what we're going to have to do is we're going to have to subtract our nucleons from our protons. Okay, and remember, your nucleons are your protons and neutrons in a nucleus. Okay, so here, as you can see, we have 241 nucleons and 94 protons. So we just go ahead and put that here. 241 nucleons, and we have 94 protons. And what you're gonna do is you're just gonna subtract that out. And once you subtract that out, what you should have is 147. Okay, so you're gonna have 147 neutrons. Okay, so with that, what we're going to want to do is start going to our atomic mass unit. So we're going to multiply our neutrons, 94, remember, okay, so our protons here, these are our protons, times 1.007825 atomic mass units. And here, you see at 1.008665 atomic mass units, we're going to use the neutrons. Okay, so we're going to here, we'll put 147, and you're just going to do the calculation. So you're actually going to multiply both of these and then multiply both of these. Okay, so when you have 94 times 1.007825, you should come out with the answer of 94.7355 atomic mass units. And then once you multiply 147 times 1.008665 atomic mass units, you should get 148.2738 atomic mass units. Okay, and with this, all we're going to do is we're just going to add them up, and we're going to try to find our mass defect. So we're going to add these here, and when you add them, you should get 243 point 243.0009305 atomic mass units. From there, we're going to actually subtract from our original atomic mass units here. Okay, so here it's going to be minus 243.0093005 atomic mass units. So once you subtract both of these, your answer should be negative 1.9524597. Alright, so this is pretty much our mass defect. And with our mass defect, what we're going to do is we're going to plug it in into our equation here. E equals mc squared. As everybody knows, it's Einstein's mass energy equivalence relationship states that E equals mc squared, where E is the product of reactants or energy, and you have mass product of reactants plus minus reactants, which is pretty much your mass, and then you have your C, which is the speed of light, which is 3 times 10. So with the number that you have here in atomic mass units, you're actually going to plug it into this equation here. So with this, you're going to have, with this, you're going to just plug it in, negative 1.95247 atomic mass units times the speed of light, which is 3 times 10 to the 8th power. It should be meters per second squared, so per second squared here. And all you're going to do is just multiply both of these together. Okay, so when you multiply everything out, you should get negative 1.76 times 10, 1.76 times 10 to the 17th power, and then your units are going to be atomic mass units times meters squared all over 7 squared s squared. So here you simply plug into your product here. So once you get this, we're going to convert to a more familiar energy unit of joules, and recall that 1 joule is 1 kilogram of meter squared per second squared. So therefore we need to convert atomic mass units to kilograms, and we can simply do that by putting delta E equals, and then pretty much what our answer here is, negative 1.76 times 10 to the negative 17. Now from here, what we're going to do is we're actually going to multiply 1 gram over Avogadro's number, which is 6.022 times 10 to the 23rd. Remember, that's Avogadro's number. And then with that, we're going to go to 1 kilogram over 1,000 grams. Okay. So here all we're doing is using the same number that we got here from our E equals mc squared. We're going to use that same answer, plug it into this equation, convert it. It's going to multiply it, or technically divide it by Avogadro's number, and then again multiply, which is divided by 1,000. And when you do that, you should get negative 2.92 times 10 to the negative 10 kilograms meters squared all over s squared. So once we get this number, we're going to find our binding energy, okay, as far as the nucleons. Now in order to find our binding energy for our nucleons, what we're actually going to do is we're going to use our nucleons number here, which provided to us earlier in the original equation, and we're actually going to divide everything here by that same number of nucleons, which is 241 nucleons. And once you do this equation, our actual nuclear binding energy should be 1.21 times 10 to the negative 12 joules per nucleon. So this is going to be our overall answer here. So just to recap, go through this a little faster. It says here, to calculate the nuclear binding energy in joules, the binding energy per nucleon for the following isotope. We have plutonium here, and like I explained earlier, our nuclear binding energy is the energy required to break up a nucleus into a component protons and neutrons. Here, what we did was we got our nucleons and our protons. We subtracted our nucleons minus our protons to get our neutrons. Mind you, our nucleons are protons and neutrons in a nucleus. From there, we multiplied our protons and our neutrons times our atomic mass unit. There, we got this equation here, added everything up. Once we added everything up, we found the difference here. Once we find our difference and our discrepancy, our mass discrepancy, we plugged into Einstein's equation. Equivalence relationship states that E equals mc squared. So here, use that same number of the difference, multiply it by the speed of light squared here. And then once you square it, you should get this answer here. Once that's done, you already know that your energy equals here, but you have to convert it to joules per nucleons. Do that by multiplying by or divided by Avogadro's number and then divided by another 1,000, which should give you a number here. Once you're done with that, and you get this number here, you want to divide by your nucleons that's provided for you, and overall you will get your joules per nucleons. My name is Raymond Stewart, and have a great day. Bye.